Hello, good morning, good afternoon, good evening, wherever you are. Thank you very much for joining this recorded episode of eCHO. This is going to be episode 188, and it's going to be all around a subject called OOM. For those that haven't come across OOM before, this is a phenomenon where your server, machine, laptop, it could be, has reached a state where it has run out of memory. So OOM stands for out of memory, and it is at this point where bad things typically will happen. In some cases, your computer will fail, or something may take over to try and fix things. So before we kind of delve into that, we'll do our regular housekeeping. As mentioned, this is recorded. This is being recorded, so it isn't up on YouTube yet, but it will be, and these notes will be updated afterwards. But as always, in the news, we have the Cilium newsletter and also a link to last week in Kubernetes development. So all of the exciting things that have been happening recently in Kubernetes. In terms of upcoming events, we have a webinar all around the upcoming Cilium 1.17 release. And then additionally, some upcoming conferences where we are starting to see a lot of people of the community kind of talking about things as well. So we kind of feel that these are important to mention. So one being the KubeVirt Summit in 2025, which is this year. That is a virtual summit, and the CFP is open now. And additionally, TalosCon. They are going to be doing their second, I believe, Talos conference this year. And the CFP is open for that as well. So let's kind of kick things off with what we're going to be discussing today. Well, first, we're going to delve into OOM killer. So what the OOM killer actually is. So as mentioned, there is a state that a machine can reach, which is called OOM, which is out of memory. And your system will either crash, panic, or in the Linux world, a thing called the OOM killer will come into play. So we're going to kind of talk a little bit about what the OOM killer actually is. Secondly, we will then talk a little bit about configuring the OOM killer. So what you can do to a certain degree to configure this technology inside the Linux kernel. Then we will get our hands dirty with some eBPF. So we will look at today what we can do with eBPF to understand what the OOM killer has actually been doing. And then in April this year, there was a patch set that was announced, which is extending eBPF with a number of additional kfunks, some helpers, etc., which would allow us to do a lot more clever things in the event that the OOM killer is triggered. So using the power of eBPF to do a lot more things. So let's kick things off with what is the OOM killer. So I'll just move over to a different window. One second. Right. So let's bring this in. So these are the kernel docs. I'm not entirely sure why some of the characters are broken, but we can skip past that. But I'll make it a little bit bigger. So as I mentioned, OOM is a state where your machine has run out of any addressable memory. Programs that are trying to do a malloc, where you allocate memory, or just trying to kind of get some more memory to do something, will find themselves in a state where simply there is no more memory available. Things will fall over, things will crash. Your machine may completely crash and panic and things like that. So in the Linux world, we have the OOM killer. And the OOM killer's job is to find a process to kill in order to retain or recall some of that memory so that your system kind of will stay up. The OOM killer is a funny implementation to a certain degree. It's often I've found there have been occasions where the OOM killer has triggered and it's done things like kill the SSH daemon. So it's managed to keep the database running, but now I have no way of actually logging onto my system to fix things or do anything. So that's why, and we'll go into it a little bit later on, being able to configure the OOM killer is very useful, because the logic that it has in order to try and free up some space is by default, it can be a bit crazy as such. So let's kind of quickly step through this kind of quite bad diagram, but we see here an out of memory event has been triggered. And when an out of memory event is triggered, then OOM kill functionality inside the kernel will be triggered. It's a case then of selecting a bad process, and that is the bad process that's going to be killed. And it's this badness algorithm that is used in order to determine which process should be killed. And some of this is how old the process is. So if it's a brand new process that suddenly appeared on the box and occupied all the memory, it could well be that the algorithm will select that one and leave everything that's been running for quite a long time up. So it looks, from a logic perspective, it looks like somebody started a big process and will kill it and return the state of the system back to running as expected. But yeah, so as you can see here, this is kind of the logic that it goes through. This is the checklist, as it were. So is there enough swap space left? If no, if yes, then we don't OOM. Has it been 5 seconds since the last out of memory failure? If yes, then we don't OOM. Has a process been killed within the last 5 seconds? Then not OOM. It's only above those tests then that the OOM kill process is actually called. And then, as mentioned, the OOM kill goes through the steps of killing that process and hopefully then saying to the system, here's some memory that's been returned back to you. So as I mentioned, there is a whole algorithm for selecting a process. And that's it. It touches a lot of subsystems, but ultimately there's not a lot to it. It will quickly try and find a process, kill that process, return some memory back to the system, and you can carry on as before. So let's look a little bit more into configuring it. Let me change this 1 second. Bring in the right window. Here we go. Sorry about that. So this is a blog post that I found that kind of explains it quite neatly, but this is what you will see in the D message or in your kernel logs, that the out of memory subsystem has been triggered, what the process ID of the program that's killed was, and what the actual command to run it or the name of the program will be. We kind of already talked a little bit about the process selection. As mentioned, like the kernel needs to ensure it has enough memory for itself. It will try and find a process that may be new or is using too much memory. And then also, as we're about to see, you can allocate a score to a process. So we have Postgres running. We want to make sure that no matter what happens on the machine, that this process is given kind of a priority. So a process with that higher score means that it's less likely to be selected by the OOM killing selection process. So we can see here, we find the PID of it, and we can see its OOM score. here in this example, we can effectively give the score a much more lower value, so that it will never reach a value high enough to be killed by the OOM killer scheduler. So that's pretty much all there is really kind of to it. We can effectively say on a PID by PID basis how likely we would like it for the OOM killer to kill that process in the event of a out of memory event. Other things that you can do if you really want to is turn off the OOM killer. This is a bad idea, I would say, because if you do that, then at some point or another, everything will potentially just fall over, and the system won't have any protection to try and save itself in the event of that particular issue. So I think that's largely kind of it. There's some other things we can basically say. Force a kernel panic on out of memory. I think that's kind of largely it. So as I say, you can see here that whilst the OOM killer is quite powerful, it's kind of a little bit hard to manage, and that you need to start your process, find the process ID, and then allocate it a score low enough so that the OOM killer won't actually, do anything with it or attack it. So you can start to see a little bit here why eBPF and being able to hook eBPF into this process would suddenly allow us to have a lot of value and a lot more control in terms of what is actually happening in the event of an out of memory event. So we've covered out of memory. We've covered the out of memory killing function within the Linux kernel. eBPF. So, as we know, and we've talked about, eBPF we can hook into various areas of a running system. And when these processes are triggered within the kernel, whether it's a network event, or in this case, whether it's an OOM killer event, we can see things and we could potentially act on them. So the first example is a bit more of a kind of a read-only K-probe. So I'll quickly kind of step to that, and we'll step through what's kind of happening in here. You make this a little bit bigger. Right, so hopefully it should be big enough for everyone. So this is a simple example of reading what is actually happening from the OOM killer here. So quickly stepping through it, we have a ring buffer. We have a struct, which we are going to use to define the various bits of information that we want to take from the OOM killer and send back via that ring buffer. And then here is the kind of important bit. This is what we are going to be attaching to. So we're attaching to the OOM kill process function within the Linux kernel. So we attach our K-probe to this, and whenever this is triggered, our code will execute first. And we can kind of see here that we will receive this struct. So this is an internal kernel struct, which has all of the details that the OOM killer is going to need and use when it is about to kill a task. So the OOM control struct will contain things like the chosen task. I think that's the main thing that we actually kind of need from it, but there's a lot more within that struct that is needed and used by the OOM killer. But the main thing that we kind of care about is the task that the OOM killer has chosen. So stepping through this, the OOM killer is triggered. We will basically print out a message to the BPF trace logs that the OOM kill process has been triggered. We are going to create an event that is going to use that task info struct up here. We're going to allocate on the ring buffer for it. And then finally, we will start to read from the kernel. So the first thing we're going to do is we are going to get the chosen task from the OOM control pointer that was sent in when this is triggered. We will then read from that the PID of the process that is being killed. This is the command of the program or the task that's being killed. So that could be /user bin Postgres or whatever, and that is then added into the task info here. We get the current task that has triggered the OOM kill. How much memory is being used by the task, and then finally we submit that task info to the ring buffer. So effectively what we're doing here is we have a ring buffer, and every time there is an OOM kill triggered, we are grabbing its PID, we are grabbing its command line, we are grabbing its memory usage, adding that to our new task info, and putting that on the ring buffer for a userland program to be reading from that buffer. This example is pretty much similar to the one that's in things like the Datadog or some of the other eBPF powered probes that will watch for memory events on a running system. So this is kind of a read-only example of doing things with eBPF. Now, as mentioned, in April, a patch set was submitted, which will allow us much more control into what happens with OOM killing events with eBPF. So let me just quickly get it's going to be hard for anybody to read, but effectively, this is free to read on the Linux Weekly News. But effectively, as we've mentioned, the OOM killer works. It's hard to configure because you need to know about things after they've been created to kind of control them. And left unchecked, the OOM killer can do whatever it wants and just kill anything and everything. So the idea in this patch set is twofold. One is to add an extension to one area of the kernel, which is called the PSI, which is the pressure on the system. So the pressure stall information subsystem. So whenever the memory usage of a system is getting too high, this will be triggered first. The second area is hooking into the it's this one here, yeah. So hooking into the out of memory so hooking in here is what's happened when an OOM kill event is actually triggered. So we have two areas that we could potentially hook into here. One, being able to set a threshold, which could be 80% of my system memory usage is being utilized. With that threshold, when we breach it, now my eBPF program will be executed. Or alternatively, when an OOM kill is triggered, or when an out of memory event is triggered, this is where our eBPF program, our other alternative eBPF program, will hook in, and it's here where our code would then execute. So there is some example code that kind of steps through this, and we'll kind of quickly go through what that would actually look like. So this is slightly easier, and this is taken from the tests that have been submitted as part of the patch set. But effectively, this program would be triggered when a pressure event has been triggered. And first off, we will be sent the PSI trigger. And it's this trigger which will contain various bits of information that we kind of need to know about. So the main thing really is getting the C group that the task is in. The second is getting the memory C group information from the C group. So, kind of what's actually in there. If we get that, then we will trigger the trigger the OOM killer for that particular C group, and then the OOM killer will kill a task within that C group. So this is a pretty simplistic example of when we hit that pressure stall. So we've breached, but 80%, for example. It's here where we will get information that we care about, and then potentially trigger a out of memory event, or we could do things like trigger something that would delete tempfs files that are also using memory. There are a number of examples and discussion taking place about what within eBPF we can do now that we can hook into these events happening within the system. The second example, which again comes from the self-tests, is a little bit more expansive, but we'll kind of quickly step through it. So this is pretty straightforward, but effectively what it does is it will find. Here we are past the same things that were passed in the kprobe example. So that OOM control struct is passed in when the OOM kill is triggered. So we need to get the root memory C group, and then what we're going to do is going to iterate through every child C group from that root C group. So using the BPF for each. So this allows us to do loops in eBPF. We're going to go through that root. We're going to go through that root memory C group and find all of the child C groups. So every time we get a child C group, we get its memory usage, we get the size of the page cache for that C group. And then a couple of things really. If the usage is more than should be used, and we know that this C group has tasks that can be killed in it, then we know that this is a victim C group. And if that is the case, then we actually have a victim to use. So what we're going to do now is, now that we have a C group with tasks in it that we can kill, we're going to use another loop, which is going to go through each of the tasks within that C group. So here we can see it's for every task that's in the victim C group, get the actual task itself. And then here we're actually calling, and this is another function that's been added as part of this patch set, is the OOM kill process. So this actually says out of memory kill the task that is part of the OC, the OOM control, and then finally release that task's data, that task's memory, so that the system is now has freer memory and can hopefully continue. And then finally return the updated C group information with its now dead task, and then update the parent C group so that the kernel has an updated set of the child C group and the parent C group with the changes that have happened that we have incurred. So we can see here two examples. One where we can effectively have control that basically says if we have a pressure event, so CPU is at X or memory is at X, then our eBPF program will trigger. Alternatively, OOM kill has happened, and what do we want to do about it? And in this event, in this example, we go through all of the C groups, looking for child C groups, and in those child C groups, looking for one that has tasks that can be killed. You can see here where we could do things like have logic, which basically says if the command of the task contains the SSHD string, or we could have a lookup on a map or something or other like that, don't kill it. So we can effectively have eBPF logic in there now, which will protect certain tasks and effectively provides us a lot more power than what currently exists in the OOM killer functionality that exists today. So I'm super excited about this. I think, I think my time working at Docker, where like the Docker engine would OOM kill its Docker containers all the time, and time working with Kubernetes, where you set your limits on your pods and they start dying, and it's kind of hard to know exactly what is occurring because, as I mentioned, the OOM killer is powerful but not very clever. And this is going to allow us to put a lot of clever logic into everything that happens when your system reaches a point of either being under pressure or has effectively hit the wall with running out of memory. So, that's everything that I kind of wanted to cover today. I'm like super excited to hopefully see this kind of functionality land in the kernel soon. And as always, super excited to see what comes next in the eBPF ecosystem. I think this is a fantastic new addition when it's ready. It's still a work in progress at the moment. But it's, again, another example of being able to extend existing subsystems within the running kernel and just make things even more powerful than they are already. So with that, I'd like to say thank you very much for joining today. As I mentioned, this has been recorded because I am going to be away for my birthday on Friday. But if you do have any questions, please find me on the Cilium and eBPF Slack. You can ask me any questions that you have there. I'm at Dan, so easy enough to find. Or just ask questions in general, and I'll try and have a look at the next available opportunity. But I'd like to thank you all very much for joining today on the session all around what is OOM, what is the Linux OOM killer, what we can see today with eBPF, and where we may be going, hopefully in the future, with extending the Linux kernel through eBPF to do a lot more things when these events are actually triggered. So thank you very much and goodbye.